In today's video, we're going to learn about static friction, which is the friction that opposes motion before it moves. So if you've ever tried to push a heavy box across a floor, what you've probably noticed is sometimes it can be hard to get the box moving. But then once you get it moving, it's a little bit easier. What makes it so hard to get the box rolling on the floor, or not rolling, but sliding on the floor, is the coefficient of static friction, which is mu sub s. Now that's a little Greek letter. It's actually the lowercase Greek letter m, and we call it mu. And generally, static friction is higher. It's greater than what we call kinetic friction. And you can see that for kinetic friction, we use mu k. K for kinetic, S for static. And the formula for that is that the force of friction is mu times the normal. Always, 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 always. Mu times the normal force. You'll see that I use a lowercase f for friction. It's just a convention. It's a way to distinguish it from other forces. Not all books do that, but that's what I'm going to use. So if it's Fs, it's static friction. And if it's Fk, it's kinetic friction. Now what's really unusual about friction is you would think that as the area gets bigger, you have more friction. And that's not the case. Friction is actually independent of the area of contact. So this is an old kind of retro picture, but I think it really shows it well. So you can see that all of these blocks and balls and chains have a weight of W. It's hard to see on the chain, but it's all the same weight. That's what we're assuming here. Maybe they're all 5 kilograms. I don't know. And they have equal weights hanging down here off the lab bench. None of them are moving. It's all equal. Because they have the same weight, because they have the same mg, they have the same normal force. So you're going to see for many of our problems that the sum of the forces in the y direction is 0. None of these blocks or balls or chains are jumping off the table. Well, normal goes up and mg goes down. So often, I don't want to say every time, but often in the problems we're going to see, the normal will be equal to the mg. I'm just showing you this because I don't want to derive it every single time. We want to make sure we can get through some material here. So it's not the area. Like I would say, all right, the block probably has the most area. Maybe the chain is second. Maybe the cube looking one is a little bit less. And think about a ball, like a bowling ball. Sitting on the table, it only has a very tiny point of contact with the table. However, they all have the same friction. Friction is independent of the area of the contact. It doesn't matter, only the overall. Now there's kinetic friction. That's friction that opposes motion while it moves. The coefficient is mu k, and it's generally less. But what's really convenient is we don't have to memorize another formula. It's the same formula. You say, what's going on in this graph? What I did in this graph was I had a wooden block, like the wooden blocks we use, and I was pulling it with a spring scale. But this spring scale, and we actually took this data from in class last year or a couple of years ago, this was connected to a sensor, to a computer. So what we see here is really two regions. We have a spike and then a lower region here. The spike is the static friction. And this is force, it might be hard to read there, on the y-axis. And this is time on the x. So it takes this big spike of force to get something moving. Like when you're pushing the box. It takes a lot more force to get the box moving than it does once it's rolling. And then once it's rolling, it settles down. And this is kinetic friction. You might say, well, why does it look like an EKG and it's real rough there? It's because it's very difficult to pull really, really smoothly. I mean, we were just pulling this by hand. We weren't pulling it like using a little car or a motor or something like that. So there's a little bit of spikiness there. That's all. That doesn't matter. The spikiness isn't important. What's important is that the kinetic friction is lower than the static friction. Now here's some numbers, and you do not have to memorize these numbers. This is the table from the OpenStax textbook. What we want to look at is the coefficients. Again, the coefficients have no units. They're just a factor. So if we look at rubber on dry concrete, static is 1, but notice kinetic is less. So that might be like a tire on concrete. If we go down to wood on wood, so that might be like pulling those wooden blocks that I have on a wooden table. Static is 0.5, but then once it gets rolling, it's only 0.3. The lower the number, the less the friction. The higher number, the higher the friction. And then once we get onto things like ice, all right, static is 0.1, kinetic is 0.03. Notice how the numbers drop and drop and drop. And that's not unbelievable because we know ice is slippery and it has very, very low friction. That's why you go ice skating or sledding on snow, which is essentially ice too. Because it has that low static friction, so you can sled really fast or you can ice skate really fast. I guess they have steel on ice here at the bottom to kind of represent if you're ice skating. So these are the coefficients. In general, if you look, the coefficients only go up to 1. They can go above 1. There's nothing that says that they can't go above 1. However, that's unusual. Most of the time for a standard physics course, unless you're doing some really crazy engineering stuff, you're going to see that if you get above 1, there's probably an issue. So what does mu even mean? It's this weird Greek letter, kind of looks like a U with a funny little tail or something on it. All mu is a measure of the roughness. That's as simple as we can say it. The higher the mu, the rougher the surface. So the rubber on the wet concrete is 0.7, but your shoes on ice, where it's very slippery, very easy to slip and fall, is only 0.1. That's why in the winter, it's very, very dangerous to drive when it's icy and snowy out because the mu goes way down. Some people will say, oh, I'm a great driver in the snow and the ice. They can't be. They don't have, the physics doesn't work. They don't have the coefficient of friction to keep them on the road. The best you can be in bad weather is a slower driver, because if you go a little bit slower, you won't have an accident. Now let's do a little math and then we'll wrap up this video. So we're going to have a 10 kilogram box on the table, and we have the coefficients of friction. Static is 0.4, and kinetic is 0.3. It's less, that's what we would expect. So if we do a free body diagram, normal goes up and mg goes down. Let's see what that tells us before we do anything else. The box isn't going to leap off the table. Unless you lift it, that box will sit on the table forever. So that tells us that the normal equals the mg. Then we're going to pull, we'll call that Fp, and friction resists. Friction is always opposite the direction of motion. Let me say that again because it's so important. Friction is always opposite the direction of motion. Friction never helps you. It only ever resists. So we're going to say, what if we pull with 25 newtons? Well, the first thing we have to see is that enough to get the box moving or not? So let's see what the maximum friction is. The maximum friction that we need to at least get when we'd need the maximum force then. The maximum pull we need to get it moving. So that's mu s times the normal. And that max doesn't make anything different. It's still just a friction equation. And we made the point that the normal is equal to the mg in this case. So now we can just substitute. To get it moving, it's static friction. We have to use the static friction, which is 0.4. They told us the mass of the box, and we know gravity. This box is not going to move until we get to at least 39 newtons. It's not going anywhere. Since we know it's not going to move, the sum of the forces, and I really should have x there, that's in the x direction, is 0. So force pull is positive. You say, why did you make it positive? Look which way it's going. It's going in the positive x direction. The frictional force is resisting. So since that's 0, the friction is 25 newtons. You say, but well, we calculated 39. 39 is the maximum. But if we pull with 25, friction can only resist with 25. It's sort of like the material knows how to resist. It's not alive. It doesn't really know, but that's what it resists with. Because it wouldn't make any sense if we pulled with 25 newtons and it could resist with 39 newtons, well, then the box would start to walk across the table by itself. And of course, that doesn't happen. So let's see one more situation, as I said, and then we'll wrap up this video. So what we see here is, let's calculate the acceleration. If we go 40 newtons, then it's going to work. So the kinetic friction is mu k times the normal, and we said normal equals mg. We could even just make a little comment over here so we remember that. So kinetic friction is always less. Kinetic was 0.3, that was the mu. Then we had the mass and gravity. So kinetic friction is 29.4 newtons. Since we're pulling it greater than 39, we said 39 is the minimum we need to move it. We're going to move this box, and we'll assume it's accelerating. So if we remember from other videos, the sum of the forces can only be 0 or ma. There's no other choice in the universe. Even if you're moving at a constant velocity, even if you're not accelerating, the sum of your forces is still 0. So those are your own, that's it. There's two choices for movement in the universe. So now all we have to do, let's see, force of the pull is to the right. Force of friction, and it happens to be kinetic in this case, is to the left. So we know the mass is 10. We don't know A. We're pulling with 40 newtons. Friction is going to resist with 29.4. So 40 minus 29, oh, that's close to 11. It's 10.6. You can divide both sides by 10. And this should be meters per second squared. Sorry, that too, it should be up there. And that's what the acceleration works out to. We'll do more with friction problems in the next video.